So we started talking about alpha carbon chemistry of carbonyls in the classroom. So now I will continue with some of the sections that follows the enolate formation through acid or base catalysis. Okay, we'll be looking at some reactions that involve the alpha carbon chemistry that we started learning in the classroom. So we know what happens when you take an aldehyde or a ketone and add a small amount of acid or base. When you add an acid, you know that a ketone or an aldehyde, it doesn't matter whether it's an R group or an H group, that can produce an enol. That's a single bond, so it will produce an enol, and it's a reaction that is in equilibrium. And the same thing, if we have, again, this could be an R or an H, which is aldehyde or a ketone, or if you add a base like a sodium hydroxide, you are going to get the enolate, again R/H. Okay, so this happens, and we already have seen how this enol or an enolate forms in the presence of an acid or a base catalyst. And now what we're going to see is what kind of reactions these enols or enolates undergo. So for example, if you take a cyclohexanone here and you treat that with a small amount of acid while having some bromine in the medium, then you'll have a substitution chemistry. You'll actually see that one of the hydrogens here is replaced by a bromine, as you can see here, and this is a good efficient reaction. As you can see, you get 65% yield, and the reaction happens through the enol chemistry, and we'll be seeing what kind of mechanism that involves. So as you obviously know that when you have an acid or a base, and also this works with chlorine, bromine and iodine, and it doesn't work with fluorine because the fluorine-fluorine bond is too strong to break, and fluorine is not going to act as a very good nucleophile. For both reasons, this reaction does not work as well. And as you can see here, the first step in the formation of the final product, which is the bromocyclohexanone, is protonation of the ketone, and you get polarization of the double bond, and that carbon center becomes a lot more electrophilic because of the addition of the proton to the molecule. And now what happens is the loss of this proton here, or the positive charge here, could be taken care of when you let these electrons make a bond, and that's how you generate the alkene moiety in this molecule, and this is what your enol structure is. So remember, when you have an acid, you get the enol. When you have base catalyst, you get the enolate. And once you have this enol, this carbon can now become the center for a electrophilic attack, and that's what happens here. So these electrons are donated to that bromine, which is the electrophile. Okay, and the other bromine leaves, as we have seen in bromination reaction involving the bromonium ion and all that in alkene chemistry. Okay, so the enol oxygen lets the electrons back, and these lone pairs can be used as a lone pair for the electrophilic bromine, and you get a substitution on that carbon center, and now this proton is kicked out again, and you get the cyclohexanone, bromocyclohexanone, and that is the mechanism for the formation of this compound. So when you have an unsymmetrical ketone like the one here, which is methyl cyclohexanone, as you can obviously imagine, both sides are possible or capable of getting a alkene group, but the one that has the alkene group on the more substituted carbon is going to be the one that is going to be more stable, because if you look at this alkene here, this is 1, 2, 3, this is tri-substituted alkene, whereas here this is only di-substituted alkene. Therefore the tri-substituted is more stable, and since this alkene forms in higher quantity, and when your bromine is coming in as an electrophile, this is the one that is going to be able to make a bond with that carbon. Therefore the major product is going to be the product where the bromine is on the more substituted carbon. So this is very similar to the Markovnikov addition that we have seen, okay, for an alkene. So you can kind of remember that to be able to remember this as well. So that's an important aspect of this reaction. And so your alpha bromination, so that's the alpha position, right? Your alpha bromination, these are both alpha positions, and as we just saw, the alpha position that is more substituted is the one that is going to be getting the bromine as the electrophile. So when you get the bromine, the product, the bromo product, can be used for to eliminate and get an alkene bond in the molecule at the carbon 2 and 3 position, okay, which is the alpha beta unsaturation. So this is the carbonyl group, this is alpha, this is beta. In terms of locant, this is 1, 2 and 3, right? So this bromine here, once you get the bromine here, right, after the first step, this is beta, okay, after the first step, once you get the bromine here and use a base like pyridine, you can very easily eliminate the bromine as HBr, which is dehydrohalogenation, which is what you have seen in the first semester organic chemistry, right? So this molecule can be very easily dehydrohalogenated in the presence of a decent base to get an unsaturation in the molecule, which is going to be conjugated. So this conjugation is one of the main reasons why this reaction, the second reaction, happens very efficiently. So once you get this, you can get the second product in very good yields as well. So other bases like potassium tertiary butoxide and even something like a carbonate, okay, can be used to affect this dehydrohalogenation step. So as you can see here, you can start with the ketone and go to the alpha beta unsaturated ketone pretty easily in one pot. This reaction can be typically done in one pot in just a sequence. So you'll take this compound or any compound you want to have the enolate chemistry or the enol chemistry, and then add bromine to that, and then quickly after the reaction is done, in the second step you will add a base like pyridine, and that reaction will undergo elimination to give you the alpha beta unsaturated ketone. Okay. So this alpha carbon chemistry, which is alpha bromination, can also be catalyzed using sodium hydroxide and bromine. Okay, just as we saw H3O plus, which is acid catalyzed bromination, we can also have a base catalyzed bromination. Of course, in this case there is only one alpha position where you can put the bromine on, because that carbon does not have a hydrogen, right? This is a CH3 group, so therefore this cannot form a double bond between these two carbons. Therefore that is the only side where the bromination can occur, and as you can see, you get a bromine on the alpha carbon on the side with two hydrogens. And the mechanism is quite simple. So instead of protonating when you have an acid, what you do is you start with the sodium hydroxide and you will deprotonate this alpha carbon, get the carbanion, and this carbanion is stabilized because it is going to have a conjugation, right? So these electrons will move in like that, and you have the enolates. That's what gives this molecule a reason to let this carbon hydrogen bond be broken heterolytically to get the carbanion. Okay, so now once you get the carbanion, this can easily act as a strong electron donor to the electrophile, and you will get this alpha substitution. So this is the base catalyzed in alpha bromo cyclohexanone formation. Okay, so under basic condition, the only thing that you will run into, which is a problem, is there is going to be polyhalogenation, right? And the reason for that is, once you get monobromination on the alpha carbon, once you get this molecule, the second hydrogen is going to be even more acidic, and the base will be able to take this off even more easily than this reactant, and therefore this now becomes an even better electron donor to the electrophile in the medium. So when you have basic conditions, you have to be really really stringent in the way you do the reaction, so that you don't get too much of the polybrominated product. Okay, so that's the outcome of an electron rich system. Okay, that's a consequence of an electron rich system. Now if you have three removable hydrogen, like a methyl ketone, okay, like a methyl ketone, you will have a reaction that goes even further. So first, when you do this reaction in one step, you're going to get a bromination on that side, because the other side does not have any removable hydrogen. So you are going to get the monobromo product, right? And as we saw, the removal of second hydrogen is going to be even more easy. Therefore this will readily give you dibromo ketone, okay, and a hydrogen. And when you put two bromines, this becomes even more acidic because of the electron withdrawing group, right? And now what happens if you have sodium hydroxide in the medium? It's going to form the enolate even more efficiently, and when you have bromine in the medium, you are going to get tribromo product. And this happens with methyl ketones. Methyl means you have 3 removable hydrogens, and that's a methyl ketone. And this happens very easily with methyl ketones. And interestingly, what happens is this reaction does not stop at this stage when you still have base in the medium, because typically when you do these reactions, you are going to have to add excess base, okay, so that the higher concentration can make this reaction work at an appreciable rate. But the problem is this reaction is now going to be even more reactive, because once you have 3 bromines on this carbon, there is a lot of negative inductive effect, which is removing electrons from that carbon, which is going to remove electrons from that carbon further through the sigma bond, which makes this carbon center a lot more electron deficient. So the hydroxide will attack that carbon, and it will give you CBr3 and that OH over there. And as you can see, these electrons will come back in, as you have seen in carbonyl chemistry, like when you have a ketone and a nucleophile like a cyanide. What happens is the nucleophile attacks there, you get CN. Now what happens is, or sorry, when you have an acid chloride, okay, a nucleophile like that, CN, these electrons come in and the Cl can leave, right? So same thing happens. CBr3, because it has 3 bromines, this carbon is able to manage a negative charge very easily, and therefore the CBr3 leaves, okay, and you end up getting that, okay, carboxylic acid. And when the medium is basic, you're going to deprotonate the carboxylic acid, get the carboxylate. But then when you treat this with acid and water, you will convert your carboxylate back to the carboxylic acid, okay. So this happens. So when you have methyl ketones, what ends up happening is you will lose 1 carbon from the molecule, okay, and you'll go from a ketone to a carboxylic acid that has 1 less carbon than you started with, okay. So this is what is called as a haloform reaction, because this molecule that you get here, CHBr3, so when you add acid, the CBr3 minus that leaves becomes CHBr3. This is bromoform. Or when you have an halogen, this is going to be called as the haloform, right? So this is what is called as a haloform reaction, because it forms a haloform as one of the products, okay. And this is a very characteristic behavior of methyl ketones. And yeah, that's the mechanism, all right, and that's the complete balanced reaction. Okay, so yeah, so that's that. And this reaction works really well, which is the haloform reaction, works really well when the other side has does not have a hydrogen that could be removed for substitution, right? As you can see here, if you have 3 methyl groups here, there is no alpha hydrogen here, which could be deprotonated to substitute a bromine with, okay. Therefore this reaction works well when only one side has a methyl group and the other side does not typically have any alpha hydrogens. That being said, if you have alpha hydrogen, this reaction still works, but it's going to be the most clear-cut reaction when you have no alpha hydrogen on the other side. So we'll be looking at more interesting reactions like aldol condensation, which will be discussed in the classroom, and also we'll be doing a lab over this. But these initial few reactions are going to be very interesting and also useful synthetically for you when you want to convert, say for example here, like a keto to an alpha beta unsaturated ketone, okay.